Okay, so clearly when x and y are both 1, z is 0. Of course, that was the premise that we started with. We've got the tangent plane at 1, 1, and we determined that when x is 1 and y is 1, clearly f of x, y, which is the z value, is 0. So the point x equals 1, y equals 1, z equals 0 is on this plane. Now, when x equals 1.1 and y equals 0.9, the tangent plane tells us that z equals what? I'd say z equals 0.2. Let's write it out explicitly. It says that, first of all, negative x plus y plus z is 0. That's the equation of our tangent plane. So negative 1 plus 1, and it should be negative 1.1 plus 0.9. If we're trying to see what the tangent plane, what the z coordinate on our tangent plane is when x is 1.1 and y is 0.9, we'd better use 1.1 for x and 0.9 for y, right? So we get negative 1.1 plus 9 plus z equals 0. So z equals 0.2. Okay. So on our tangent plane, if we move from the 1, 1 point to the 1.1, 0.9 point, z goes from 0 to 0.2. Now, the actual value of f, and let's just talk just a little bit about how this works. You know, if you have a curve and a tangent line at some point, that tangent line stays really close for a little while. But then it starts getting further and further away, and your tangent line no longer gives you a good approximation to the value of the function that's represented by the curve. Well, similarly, in 3 dimensions, and this is probably not the time of the day for me to try to sketch something in 3 dimensions, but in 3 dimensions, what you have is you have this paraboloid. You come out 1 unit in the x and 1 unit in the y, and actually this isn't a paraboloid, this was a paraboloid, okay. This has a more complex shape. So if you imagine the paraboloid, and I was going to do this with the paraboloid. Okay, paraboloid is like this. At the point 1, 1, paraboloid is up here someplace, and it's got this kind of shape, so the tangent plane might look something like this. Well, that tangent plane is going to stay close to the paraboloid for a little while, for a little ways. Okay, so if we move from the point 1, 1 to the point 1.1, 0.9, we've only moved less than 2/10 of a unit. So we would expect to still be kind of close to the actual paraboloid. Now this isn't a paraboloid, this is a more complicated curve. And we could sketch it, we could do contour lines and all kinds of stuff, and you know how to do all that, so you can. But whatever this shape is, at the point 1, 1, 0, which is on the graph of this function, the tangent plane is this, and the value we get on the tangent plane should be close to the value we get when we evaluate the function. So, on the tangent plane, we find that if x is 1.1 and y is 0.9, z is 0.2. Let's see what the actual function, this more complex function, tells us. Well, it tells us that if x is 1.1 and y is 0.9, we do the evaluation, and we get 0.99 times 0.2, which is 99% of 0.2, so that this approximation differs from this one by only about 1% of the actual y value. So
if you just
this
go straight ahead, that's where we're going to eat.
Is the actual value. The 0.2 that we got from the tangent plane was off by about 1%. It was a little bit high.
Okay, good.
Now, if you want to think about the arithmetic I did here,
Oh, really?
you know, how did I get from here to here to here? And, you know, it's kind of interesting to, you know, think about this. Both this
So,
term and this term contain 1.1 times 9.
I'm gonna sign a cheat.
So I could factor out 1.1 times 9, leaving me 1.1 here and leaving me a 0.9 here. So I have 1.1 times 0.9, which is easily calculated as 0.99, multiplied by this difference, 0.2. Okay, in any case, we verified that for this particular function and this particular point, the tangent plane, if you move just a little ways from 1, 1, in other words, if you move a tenth of a unit in the x direction and a tenth of a unit in the negative y direction, that gets you from 1, 1 to 1.1.9. The tangent plane will be 0.2 units above the xy plane. The z value will be 0.2 on the tangent plane. On the actual function, it'll be just a little bit less than that. Of course, we can multiply that out. That's a 1.98 instead of, and then 0.198 instead of 0.2. So the value estimated by the tangent plane is a little higher than this by 0.002. Meaning, of course, that in the vicinity of this point, we should start suspecting that the graph is concave down, since the tangent plane stays above the curve. Of course, we don't know for sure what happens in each direction. Could be a saddle point, could be all kinds of things. And of course, we'll learn to analyze that very shortly. It's not hard to analyze. Okay, so anyhow, our tangent plane gave us a good approximation. This is how you get the tangent plane. That's how you think about the tangent plane. And whatever I was thinking when I thought I didn't do everything right, don't think that.